Hello, I'm Richard and one of the Quality Methods team based here in Oxford in the UK. This short course is the basics of DPMO, Defective Parts for Million Opportunities. DPMO is closely linked to PPM, and you will hear a lot about PPM as well as DPMO in this course. Package manufacturing has used PPM as a key performance indicator for many years. It works well, focusing on a single parameter in a process, such as flange width in a can or the E diameter in a cap, and so on. Indeed, I've encouraged my students for many years to use PPM instead of capability, because I find PPM less ambiguous as a measure of quality. Yep, I can hear you shouting at me that you need to carry out a capability study in order to estimate PPM defective. Well, yes, okay, but the questions about PP, PPK, or CP, or CPK, or CPM is all rather complex, whereas PPM is a simple measure of quality with which we can make direct comparisons for standards, contracts, and the like. But now is the time to welcome DPMO into the packaging world as a close relative of PPM. DPMO is a statistic that combines the PPMs of several parameters. So an overall view can be taken of a product with several important parameters. PPM, however, is a statistic for an individual parameter within a product. Some people must continue to use PPM because of their interest in the occurrence of specific parameter defect types. Indeed, you can imagine a problem-solving workshop to improve the DPMO, and you ask, why is the DPMO too high? Because the PPM of the outside diameter is too high. Why is the PPM too high? And so on. But the sales manager and his customers will be interested in DPMO to compare overall quality. A plant manager also will use DPMO because he is interested in knowing which lines perform best. The Six Sigma people introduced DPMO in the late 1990s, some 10 years after Motorola had introduced Six Sigma. They were driven by non-manufacturing processes needing a measure of quality. R&D projects, call centers, surgical environments, government departments, logistics companies. And here, Amazon are very strong on DPMO, and all those industries where PPM was not appropriate. So PPM and DPMO are two different statistics, although very closely related. There will be 5 topics covered in this presentation: the definition of DPMO in its simplest form, the objectives or how DPMO is used by various groups, how to calculate the statistic PPM, which is needed for calculating DPMO. We then look at the difference between the observed and expected PPM. You need to understand this difference. PPM and DPMO are used to predict the quality of products, and the observed statistic can be very unhelpful. Only then do I look at an overview of how to calculate DPMO. This short course is good enough for simple examples. And there is a further course to look at the detailed process to calculate some of the more challenging examples of DPMO, how to decide on sample sizes, also to reveal some of the donkey traps, as I call them, easy mistakes that can be made, which would leave you with false, unhelpful, and dishonest results. First, let's look at the definition. Before we start working on the DPMO statistic and predicting the quality of our process, we need some definition of what we're talking about. Let's look at a very simple example. Later, we shall develop this into a more useful application. So imagine that in a delivery of 30,000 cans, the customer finds 6 to be defective. Using ppm terminology, this equates to a defect rate of 200 ppm. Number of defects divided by sample size times a million. 6 divided by 30,000 times a million is 200. But if it had been agreed with the customer that there are 5 critical parameters in the can: height, free of scratches, top wall thickness, enamel rating, and free of print errors, although there were 30,000 cans delivered, in that delivery, there were 5 opportunities in each can to find a defect. 5 times 30,000, a total of 150,000 opportunities for a defect to be found. The 6 cans rejected by the customer had the following defects: can 1 for top wall thickness, out of spec; can 2, enamel rating high; can 3 had 2 defects, a scratch and a print defect, and so on. So there were 8 defects spread across 6 cans. DPMO is number of defects divided by number of opportunities times a million. 8 divided by 150,000 times a million, 53 DPMO. Very different to the ppm result of 200. Before we look at the objectives of DPMO, let's recap on a few fundamentals of any data analysis or statistical work. The objective of any statistic is to understand the process better. This allows us to take appropriate action to improve the process, reduce waste, reduce cost, improve the quality, make the job less stressful, increase runtime. Secondly, there is little purpose to measuring and preparing a statistic if no action is to be taken from the analysis of that data. And lastly, it's dishonest to prepare a statistic using inappropriate data, and so mislead those who use the statistic to make decisions, whether this is done knowingly or unknowingly. In the second of these lectures, I shall discuss some of the errors that are made in preparing DPMOs that lead to dishonest reporting. There are several objectives of DPMO, depending on your needs. These will be very different depending upon which part of the operation you work in, or if you're a customer of the process. There are 2 objectives for the customer. Firstly, to compare different suppliers, possibly when choosing a new supplier or negotiating a new contract. Remember, there's plenty of evidence to show the lower costs involved in using low DPMO products compared with high DPMO product. You can hear it in the factory, the purr of the can lines, rather than the clatter. And secondly, to monitor deliveries from a supplier, checking there is no significant change from one delivery to the next. Here's a typical time series chart of the DPMO values at successive deliveries, highlighting one which went out of control. This could also be an individual's chart with control limits. The manufacturer will use it for another reason, possibly within a factory to compare lines and prioritize improvement work. On the left here, you can see lines 7 and 12 are scheduled for action by the plant manager, or at headquarters to define where the best practice for the group is to be found. On the right, you can see how headquarters can see where the best potential best practice should be taken. Whereas the statistic ppm has been invaluable for the technical people to understand and predict the quality of a specific parameter of a process, such as can height, top wall thickness, and so on. For some reporting, there is just too much information to try and absorb the ppms of a dozen different parameters in your head. DPMO is useful to consolidate a group of ppms. As we've just seen, other people in the organization need a wider understanding, a more general view, such as how does line A compare with line B? Or how does the French plant compare with the Dutch plant? And DPMO allows us to do just this. We can provide a statistic which talks about the overall quality of a group of parameters, rather than the quality of a specific parameter. It's not all good news. Remember, combining ppms to provide the DPMO will treat all the defects as being of equal importance, unless we use a different DPMO for different grades of defects. Here's a table comparing overall quality of cans from 3 plants, but separating the quality into 3 types: critical defects, major defects, and other less important defects. Note that as we're talking here about predicting the quality of all the cans produced, from measuring only a sample of the production, the confidence intervals of our prediction are included. What do I mean by confidence intervals? Well, at plant A, the critical DPMO is calculated at 15, but the true DPMO is likely to be somewhere between 2 and 42. And when I say likely, I have calculated this range to be 95% confident. It will be between 2 and 42, 19 times out of 20. It's an important aspect of DPMO to have a documented, well-defined and agreed specification, both of the dimensions and of the acceptable, unacceptable product characteristics. Each of these defect types must be classified as either critical, major, or other. You may want to include more classes. If one supplier or plant uses different criteria for what is defective, then clearly any comparison between them is meaningless, and one objective of DPMO is lost. Some industries do have recognized standards to define defects. Printed circuit boards use IPC 7912A. The can-making industry publishes dimensional specifications, but I'm not aware of attribute standards, which are needed for DPMO. Some of the big food manufacturers do set up complaint protocols with their suppliers defining defect categories. The statistic DPMO is calculated using a group of individual ppm statistics. The method for producing the ppm statistic with variable data is different to the method used to produce the ppm statistic for attribute data. But for both, it is all about counting. When we first went to school, we learned to count. It was easy. But the more we learn about counting, the more complex it becomes. In package making, we cannot inspect every piece we manufacture. So we predict the total number of defects based on inspecting a sample. This asks the question, what confidence do we want in our prediction of defects? What about 50% confidence, when only half the time we're right? Would the customer accept that? No. But a well-meaning supplier who does not understand the issue may provide just this, and the customer may believe this is the true ppm or DPMO until there is some kind of issue, and then the truth comes out. Sadly, this fundamental question of what confidence do we need, which defines the whole process we use to prepare a DPMO, is more often than not ignored. You would hate having me as a customer asking questions about the trustworthiness of the ppm, DPMO result you supply. Let's just recap on the two types of data which we learned about as children. Variable data, measuring something with a gauge. A vernier, to measure the diameter, or a balance to find the weight, or a pressure gauge to see when a can deforms. The result will not be a whole number. And attribute data, counting things, the number of occasions when something has happened, the number of scratches on the can, the number of print defects, the number of leaking cans. Sometimes we even count the number of cans within or outside specification. The result is always a whole number. First, let's estimate the ppm when using variable data. This is when we measure something and the result will be somewhere on a scale. Often, the challenge is having gauge systems that are sufficiently accurate and precise, not the number of samples. For variable data, we take perhaps 50 samples from a single stable process. We shall define stability in part 2, but you can see in this chart of the data shown here, there are no points outside the control limits. Once stable, we can confidently carry out a capability study. Hello, I'm Richard and one of the Quality Methods team based here in Oxford in the UK. This short course is the basics of DPMO, Defective Parts for Million Opportunities. DPMO is closely linked to ppm, and you will hear a lot about ppm as well as DPMO in this course. Package manufacturing has used ppm as a key performance indicator for many years. It works well, focusing on a single parameter in a process, such as flange width in a can or the E diameter in a cap, and so on. Indeed, I've encouraged my students for many years to use ppm instead of capability, because I find ppm less ambiguous as a measure of quality. Yep, I can hear you shouting at me that you need to carry out a capability study in order to estimate ppm defective. Well, yes, okay, but the questions about PP, PPK, or CP, or CPK, or CPM is all rather complex, whereas ppm is a simple measure of quality with which we can make direct comparisons for standards, contracts, and the like. But now is the time to welcome DPMO into the packaging world as a close relative of ppm. DPMO is a statistic that combines the ppms of several parameters, so an overall view can be taken of a product with several important parameters. ppm, however, is a statistic for an individual parameter within a product. Some people must continue to use ppm because of their interest in the occurrence of specific parameter defect types. Indeed, you can imagine a problem-solving workshop to improve the DPMO, and you ask, why is the DPMO too high? Because the ppm of the outside diameter is too high. Why is the ppm too high? And so on. But the sales manager and his customers will be interested in DPMO to compare overall quality. A plant manager also will use DPMO because he is interested in knowing which lines perform best. The Six Sigma people introduced DPMO in the late 1990s, some 10 years after Motorola had introduced Six Sigma. They were driven by non-manufacturing processes needing a measure of quality. R&D projects, call centers, surgical environments, government departments, logistics companies. And here, Amazon are very strong on DPMO. and all those industries where ppm was not appropriate. So ppm and DPMO are two different statistics, although very closely related. To have confidence in the results, the number of measurements we need for variable data is small, at least small in comparison with attribute data. If we carry out a capability study, we may take 50 results. Yeah, here there is one piece which is out of specification, below the lower specification limit. We can see that. And this one out of specification piece will be the basis of the unhelpful observed ppm, which here is 1 in 50, which is 20,000 parts per million defective. The software uses a fitted distribution curve to predict the ppm defective for us. Here, it's 12,224, different from the 20,000. Or, by knowing the pp and the ppk, we can use tables. Here's a table which can give us the estimated result. We can see that pp and ppk can lead us to a predicted value, here about 13,000. Again, very different from the observed result of 20,000. Now let's look at a product parameter which is measured with attribute data, such as dents in the can. We need a large sample if we are to predict the ppm and subsequently the DPMO. This block represents 10,000 pieces. It's 100 by 100 cells in an Excel worksheet. Remember that your customer will expect quality probably about 63 parts per million. But I am illustrating 1,000 parts per million defective, much worse, by randomly putting 10 defective pieces, the black spots, into here. If you did not know how many or where the defects are, imagine the sample size you would need to provide a representative sample of the quality. It's tough, even at 1,000 parts per million. Imagine if there was only one black defect here. You can see how taking a random sample of 20 will be of little use, most likely containing no defect, so you would predict 0 parts per million defective. Or in the unlikely event, your sample contains one defect, you would predict a quality at 50,000 ppm. Not helpful. For the moment, for attributes, just say, let's say, if the sample size is large enough. We shall look at deciding on suitable sample sizes in part 2. Provided our sample is large enough to be representative of the process, we calculate the ppm by first preparing the statistic proportion. ppm formula for proportion is simple. The number of defects divided by the sample size. Then we multiply the proportion by 1 million. We will find a defect in one sample of 5,000 cans. So 1 divided by 5,000 times a million is 200. We do this for each of the parameters to be included in our final DPMO. To calculate the confidence intervals around this result, we use the statistical procedure called one proportion. This produces the observed proportion with confidence intervals, which predicts the minimum and maximum likely ppm defective in the delivery as a whole, not just the sample. If the confidence intervals are so wide as to make the results of little use, you'll have to collect more samples to reduce the width of these intervals. For example, if we have a sample of 952 cans from which one defect is found, the observed ppm of dented cans is 1050, with a lower confidence interval of 27 and an upper confidence interval of 5839. So somewhere between those two, the true defect rate stands. With such wide confidence intervals, the ppm is not very useful. We just need a larger sample size. This brings us nicely to the topic of observed and expected. Be patient. We shall get to DPMO shortly, when we shall use the results of ppm defective to provide the DPMO. Now, the package making industry is unusual in that it produces large quantities of pieces, whereas many industries measure their output in hundreds per day or even thousands per day. Packaging industry uses millions per day. As I've started to show, this provides special challenges in our sampling plans. Apart from the challenge of ensuring the samples are truly random, there is also much to be considered in deciding how many samples we take. Most software packages show observed and expected. Observed is a simple count of the number of defective pieces, or those that are below or above spec limits. It's a measure of the quality of the sample. It is not a prediction of the quality of the process, nor a prediction of the quality of the lot from which the sample was taken. For the estimated statistic, good use is made of the measurements provided to squeeze the data and use data analysis methods so a prediction can be made of the quality of those pieces not measured, of everything. We want a prediction of the whole lot from which the sample is taken, not just a measure of the sample itself. Let's look at a summary of observed and expected results for the two types of data, variable and attribute. First, be careful in using any statistic which is called observed. An observed variable ppm is of little use to us. As I said, it's a measure only of the sample taken. Likewise, to an extent, for attributes, which are unhelpful, but used in AQLs, and I shall look at that in part 2. Expected variable results, they predict the defects in the whole population, just what we need. But as always, the confidence we have in the result is dependent upon how well the sample represents the whole. For attribute data, we need to take a very large and representative sample. Then we use the confidence intervals to understand if the true ppm could be less than the contract or some other product. So we need to use the expected statistic for ppm where we can, because our interest is in predicting the quality of the whole delivery or the process. Let's look in a bit more detail at the observed and estimated ppms for variable data. The observed is a measure of the sample only. So to suggest it typifies the process is dishonest. It may significantly over or underestimate the true level of defects. 50 years ago, it was useful when defect levels were 5 or 10%. It ignores all the data associated from what is good, from which we can learn a lot. It's a very inefficient statistic. The estimated, however, is very useful. It requires few samples, 50 perhaps, which can be taken from the control check data. So no additional work is required. It provides good confidence in that result to be close to the truth. But do include the confidence intervals in any report you make. If they appear too wide, you know you need more data added in. Here is an example for an observed variable. We measure the height of 50 cans, whose specification is 100 plus or minus 5. Here's the data sheet with the one out-of-spec measurement highlighted. Therefore, the observed ppm, the one piece outside, divided by the 50 sample times a million is 20,000. Look at all that data we've collected, and we just used one piece. What a waste of data. Let's take those 50 samples again, 50 results, and plot them, and then fit a distribution curve. You can see the defective piece there, which we can also predict the ppm by measuring the area under the curve below and outside the spec limit. If the total area under the curve is 1, the area to the left of the lower spec limit is 0.0141 or 14,100 ppm. Because the fitted curve is based on a sample, we can fit confidence limits around this. And the lowest is 3,500. We've seen the mid one at 14,100, and the upper is 18,000, different to 20,000 parts per million on the observed result. Now, for processes that produced non-normally distributed data, we can use the same approach. I know it's more difficult to handle non-normal data, to find a suitable distribution, but that's a different subject to today's ppm estimate. So for a product from a process whose measurements provide non-normal distributions of data, for example, enamel rating, it's the same approach. Plot the data, fit the curve, calculate the area under the curve in the tail outside the spec limit. This example shows 60 results from an enamel rating study. The unhelpful observed result, using just one piece of data, suggests a ppm of almost 17,000 ppm, while the expected area under the curve to the right of the USL is 14,500. There are examples where the observed will underestimate the ppm defective. But the learning point is that observed results are unreliable. Now we can look at some attribute data, where the challenge is having sufficient samples. If we're going to deliver 10,000 cans, how many samples should we take to check that the quality meets the contract? In this case, less than 1,000 ppm defective, or in this case, less than 10 cans in the delivery of 10,000. Under observed data, the calculation for ppm is simple. The number of defects divided by the sample size times a million. But it will be dishonest if n is small. Only when n is large, when you are using cameras or vision systems to collect data, can we begin to get reliable reports on ppm. Oakland suggested we convert attributes into classifications and then use them as variables. Indeed, I remember giving my quality managers an annual objective one year to convert one attribute into a variable. Estimated or predicted, just have to have large sample sizes. The formula in the title here refers to the relationship between n, the attribute sample size. We would have used a small n for a variable sample size. C, the width of the confidence interval required to ensure the top of the upper range is less than the customer contract. and alpha, which is the confidence in the result. These are linked. Let's think for a moment about the level of confidence you need in a result. Imagine that you are told there must be 95% confidence in the ppm reported being less than 2,700. Clearly, this is an important delivery. Or you may be told, as the line improvement project will address all lines in the next 12 months, we only need 80% confidence in the ppm reported. Not so important. It's just a guideline to help people. The outcome is not too drastic. How confident are you that the true ppm respects the customer wishes? Have you taken enough samples to be confident that the top of the upper confidence interval is lower than the customer contract? Suppose that the customer contract requires 90% confidence that the true ppm is less than 2,700. On day one, we collect 5,000 samples and find 6 defects. The observed ppm, 1,200. Here is the 90% confidence band, and the upper limit is less than 2,700. So we are 90% confident that the true ppm lies somewhere between 523 and 2367. We are respecting the customer contract. Day two, we only collect 2,500 samples and find 3 defects. The observed ppm is the same, 1,200, but now the upper limit is outside the customer contract, with a range from 327 to 3,100. In fact, we only have 80% confidence that the true ppm is less than the contract requirement of less than 2,700. So we learn, high confidence requires lots of samples. If you only have a few samples, you'll probably have low confidence in the results. Another way of looking at it, again, how confident are you that the true ppm is close to the observed ppm? Customer contract defined a ppm required of less than 2,000. The control check collected 5,000 samples, in which 6 defects were found. Let me mention here that all these confidence bands you're about to see relate to the same sample and same number of defects. We're just looking at different levels of confidence for the same control check. The observed ppm for 6 defects in 5,000 is 1,200. Looks like we're all well within the contract, but 99% confidence, the true ppm lies somewhere between 300 and 3,200. It's not good enough. We may be delivering outside specification. We can be 95% confident that the true ppm lies between 440 and 2,600, and so on. It's only when we reduce the confidence to 70% that we can say we now know the true ppm conforms with the contract. That means only 2 out of 3 occasions we shall be correct and deliver with a defect rate less than 2,000. On the other occasion, we may deliver product with a defect rate greater than 2,000, or we may isolate stock thinking it's worse than 2,000 when it's good. And as confidence drops, the band shrinks. As has been said, for attribute data to have confidence, we need very large sample sizes. Reducing the width of confidence intervals so we can meet a customer contract means we must reduce our confidence that this is the true ppm. 70% means being correct only 2 out of 3 times. Once we have estimates for the expected ppm, variable parameters from a capability study, attribute parameters from the proportion statistic. We can start to combine the ppms from the various parameters to create our DPMO. Before we combine the separate ppms to build the DPMO, we have a few decisions to make. Not all parameters are equal in their impact on quality. This is a subjective aspect of the process to be made by the people who will use the data to make decisions. Parameters can be classified critical, major, important, other, or some other classification that's used in the business. Or parameters can be weighted, times 10 for important, times 1 for least important, or some other scale which is easy, but helps to differentiate between the critical and non-critical. The solution to combining all the different parameters of different importance comes in a simple database of the individual ppms you have prepared. Here is a simple example. On the left hand is the source of each ppm. Factory line, date, parameter, and so on. You enter the ppm and the confidence limits for each parameter. You enter the agreed weightings for each parameter. 4 for top wall thickness, 7 for print defect, and so on, or whatever you use. You total the weightings. 4 plus 7 plus 6 plus 3 is 20. You multiply each ppm and its confidence limits by the weighting you allocated. You add each column of the ppm times weighting. You divide each total by the weighting total. So 3568 divided by 20 gives a DPMO of 178.4. So now you can report the DPMO with its confidence intervals. By storing the data in a simple database, you can group whichever parameters together you wish to report. Report by plant, by line, or by parameter. So you have the individual ppms for each parameter. It's easy to combine them into your DPMO. You decide which grouping is useful. Before we finish, an important aspect of this topic. In this lecture, I have said it's dishonest to prepare a statistic using inappropriate data, and so mislead those who use the statistic to make decisions, whether it's done knowingly or unknowingly. How well the sample represents the whole is important. If it doesn't represent it, it's no good. And 50% confidence means you'll get it wrong half the time. And you must have a sample which is large enough to be representative of the process we're measuring. Well, I hope you have found this useful. The objectives, how important it is to understand ppm so we can create the DPMO, the dangers of observed results, the importance of confidence intervals, and once you have the ppms for each parameter, how simply they can be combined to produce the DPMO for whatever group of parameters you wish. In the second lecture about DPMO, I shall be looking at sample sizes to ensure you have adequate confidence in your result, discussing those 5 criteria to respect so your results are honest. These 5 are known to your customers and you may get audited on them. We'll look a little more at the detail to calculate the unusual ppms. Consider the 6 Sigma standards for DPMO by industry. So thanks for listening and catch up soon. Bye.